Hello everyone, my name is Anwar Lamza and today I will be doing my lab presentation for the control volume. So for the introduction, control volume is a volume in a space surrounded by imaginary boundaries through which fluid might flow. Control volume approach is there's three type of control volume approach, which is through mass, momentum and energy, or we can say all energy. Today for this experiment we will focus on momentum approach. So what we need to know, the important thing when we say about control volume approach of momentum, we will say that sum of force equals sum of rate of momentum minus sum of rate of momentum out. Rate of momentum in equals to rho density times velocity times area times velocity again. So our objective for this experiment is to understand how force is related to the rate of momentum flow in jet. And the second one is how theoretical computation of momentum differs from force measured of the water jet. So this is the experiment and calculation setup. As you can see, this is our setup. So water jet will come to here and shoot up this thing, and as a result, it will displace the jockey weight, and we can see, and we can take the measurement and compare the momentum from the nozzle or from the water and compare to the force. So basically we already know, we decide what's the jockey weight and everything. And this is our equation, general equation. I mean, it can be simplified if we has beta equals 0 or 90 degree or 180 degree for flat plate. And this is our boundaries, our imaginary boundary as said before. So for max plate, what we expect is force equal to the momentum, which is we denote here is J. And for the hemispherical cup, we expect F equal to J. So for the procedure, apparatus is level and the lever is brought to balance position with jockey at its zero setting. Water is admitted through the bench supply valve and flow rate increased to maximum. Reduce the flow rate at the interval and make observation and take reading. So basically from max we take reading, then we slow it, take reading slow. About 8 observation is enough for this. We will run it twice, first for a flat plate and second for a hemispherical cup. So the result here is, this is what we get. So basically this is all the data we get. This is the displacement. This is, so what we want to do is to compare the momentum and the force, which is supposed to be equal if we talk it theoretically, which is basically the momentum that's coming equal to the force that opposes it, and the force that opposes it is based on jockey weight and its displacement. So if you plot it, you can see this is the hemispherical cup slope and this is a flat plate slope. So this is the flow rate, this is the one that we get. This is the one that we apply to the jet, and basically this is what we calculate using formula that I mentioned before. This is to calculate the momentum, and this is the force we calculated from the jockey displacement, jockey weight displacement. So we want to compare these two. So what we're saying is, if it's theoretically true or it's ideal situation, this will equal to this. So that's why we plot this graph. The graph is force value over flow in jet J, as we F equal J for flat plate and F equal to J. Based on the plot, we do a line of best fit. This is a line of best fit, as you can see. This is also a line of best fit. And for flat plate, the slope of graph is 0.97. So our max is 1, which is essentially saying that F equals J. And for hemispherical slope, we get 1.97, which is we saying that F equals 1.97 J. But the theoretical, or what we say is max, is 2. So we can discuss here that what can be the causes of this value to reduce from theoretical or the maximum value. So what we can say is the loss can be due to human apparatus error, or apparatus error, such as for human error, is error in approximating the nozzle diameter or reading the displacement. And for the apparatus error is maybe the flat is not flat enough, or the flat tolerances in manufacturing is not flat enough for us to mathematically consider it as perfectly flat. So that's all for my presentation. Thank you.